Okay. Um, Welcome to the second presentation in the fifth webinar series presented by the International Absorption Society. The IAS is an international organization dedicated to advancing absorption as a solution to scientific, engineering, and human welfare challenges through the promotion of absorption research and education. We thank everyone for attending the webinar today. The webinar series has been an immense success, and the recordings of previous webinars continue to be viewed on YouTube and Bilibili. This is the second webinar of our fifth series, which we will continue to have monthly throughout the year. We intend to continue with a variety of speakers from industry, academia, and other research institutes, as well as PhD students and early career researchers. Announcements regarding the fifth series will be distributed through IAS mailing list and the IAS Twitter feed, now X feed. Today's webinar will be given by Dr. Li-Chiang Lin at National Taiwan University in Taipei, Taiwan. I am Yongchul Chung at Busan National University in Korea, and I'll also moderate today's webinar. We are required to remind attendees and future viewers that the views expressed by the speaker, host, or other moderators are not necessarily those of the IAS or the institutions associated with those individuals. We ask that you consider joining the IAS as a regular member if you are not already. Our dues are minimal, only $20 per year, but support the publication of our flagship journal, Absorption, contribute to travel grants and workshop seed funding for IAS members and affiliated groups, as well as aid the organization of our triannual conference on the fundamentals of absorption. Members also receive free access to IAS-supported materials, including our journal, as well as the absorption database published by Springer Materials. Anyone can follow the IAS on X at INTADSSOC for future updates regarding IAS events, webinars, and information about scientific meetings. Please help us expand our YouTube channel by liking this video and subscribing. Now, it is my pleasure to welcome Dr. Li-Chiang Lin to today's webinar session. Dr. Li-Chiang Lin received his PhD degree in chemical engineering from the University of California, Berkeley, and conducted postdoctoral research at MIT in materials science and engineering. He is currently an associate professor in the Department of Chemical Engineering at National Taiwan University. He also holds an adjunct associate professor position in the William G. Lowry Department of Chemical and Biomolecular Engineering at The Ohio State University. Before he joined NTU in August 2021, he was formerly an assistant professor at Delft University of Technology, followed by an appointment as an assistant professor and the inaugural holder of the Umid S. Ozkan Professorship at OSU. His research of interest lies in the computational materials field. He applies and develops computational methods to study porous material for their potential in energy-related applications, such as gas separation. To date, he has published 120 peer-reviewed articles with a total Google Scholar citation of 7,000 and an H-index of 41. He received several awards, such as the 2023 PCCP Emerging Investigator Lectureship Awards, 2023 Ta Yu Wu Memorial Award, 2023 Academy Advancement Award, and 2022 Outstanding Young Scholar Awards, and many more. Sorry, it's a little bit too long of the list. He also has been included in the world top 2% of scientists list for four consecutive years. Besides, he also received the highest teaching honor from OSU and 2021 Alumni Award for Distinguished Teaching. During the webinar, questions can be submitted to the speaker as comments on the YouTube live stream. Questions will be answered at the end of the presentation. With that, I'll welcome Dr. Li-Chiang Lin again and pass over the presentation to him. Li-Chiang, yeah.
Yep, thank you, Greg, for your kind introduction. And let me share my screen. Could you please stop sharing? Okay, so let me click the screen sharing. Right. Can you see my screen now?
I can see your screen, yes.
Okay, so let me pull out my pointer. Sorry, just give me a few seconds. Okay. Pointer. Yeah, I just want to make, okay. So I guess you can, Greg, can you see my pointer? Just want
I can
to
see your pointer.
Oh, cool. Yeah. Thanks again for the kind introduction, and it's really my great pleasure to be the speaker for today's webinar, and thank you for watching. For today's talk, I would like to share with our recent research. I probably shouldn't say, I mean, most recent, but years of research result in the area to determine surface area for porous materials. So in today's talk, I will talk about our systematic evaluation of the widely used BET method. And I will also like to talk about our developments we develop a machine learning model to help us to inform the accurate BET surface area. As Professor John kindly introduced, my name is Li-Chiang Lin from National Taiwan University. And I would really like to take this opportunity before introduce the research and to talk about our institution really, really briefly, I promise. As you may know, NTU, National Taiwan University, we are located in Taiwan, shown here. We are pretty close to China, Korea, and Japan. And NTU is located in the northern part of Taiwan, which is the Taipei city, which is the capital. And if we have a closer look, and Taipei capital is actually inside of what we call New Taipei City. It's surrounding the New Taipei City. So NTU is located here in Taipei City, which is actually pretty close to the Taoyuan National Airport. If you ever visited Taiwan, I believe that you will land at this airport and you can take metro system to NTU campus, probably within like 1 hour, which is really convenient. So some statistics about NTU. NTU was established about 100 years ago. We have more than 2,000 faculty members, more than 3,000 students, 30,000 students, sorry. So we are one of the biggest universities in Taiwan. And we have 16 colleges, and also more than 50 departments, etc. And I also want to mention that we also have a really strong medical program. So we also have one hospital. So according to the ranking, QS ranking in 2023, we are ranked as 77, which is pretty nice. So I want to show you one of the pictures of NTU campus, and I would say NTU campus is really beautiful. So if you ever visit Taiwan, or if you want to visit the campus, you can feel free to contact me. And this is the main boulevard on the campus. So upon entering the main entrance, you will see a really, really long boulevard shown over here. This is the main library. Although sometimes it could be quite a bit hot during the summer, but this is really beautiful campus. And our building is actually one of our buildings is actually located here, which cannot be seen clearly. So about our department, we have more than 37. We have more than 35 faculty members, exactly 37 faculty members, and we have, as shown over here, every year we have more than 100 undergraduate, more than 100 master, about 20 PhD. We have 2 buildings. One is fairly new, which was established about like 4 years ago. And we have so many faculty members, and they are doing a diverse research area, as shown over here. And apparently, I'm doing computations. Actually, I should mention this earlier. So my research concerns mainly about computation. I only do computer simulation, but I will argue we are trying to do experiments using simulations, which you will see later on. My research, or many of you guys' research, lies on porous materials. So as we all know, porous materials like zeolites or metal organic framework and many more, they have many interesting properties. So given there are so many excellent IAS webinars on YouTube already, and have many talks talking about it, so I would like to keep this brief. So they have many interesting properties, like they can offer selective adsorption. This is adsorption isotherm, uptake burst pressure. So given CO2 has a stronger quadruple moment as compared to nitrogen, so CO2 normally will tend to adsorb stronger, so they have higher uptake at a given pressure as compared to nitrogen. We can use the difference to conduct selective adsorption, selective separation. So they can also have really high surface area, which will be the subject of study in today's webinar. So they can have really large surface area, so we can use the materials to provide area to store gases. like hydrogen storage, methane storage, etc. They can also offer selective permeation, like we allow one component permeate faster than the other, as shown over here, so they can be used as a potential membrane candidates. Last but not least is that they have really huge tunability, as you may know. Like zeolite materials, they are built by tetrahedral SiO2, but they are also aluminum silicate zeolite materials. That is to have aluminum instead of silicon. Nonetheless, they are already about 250, 240 distinct topologies has been reported for zeolite materials, as shown over here: CRB, DFT, SOD, etc. They can have small pore, large pore, different channel connectivity. And if we further talk about, you have different silicon to aluminum ratios, like as I say, aluminum silicate zeolite materials. And given this is 4+ versus 3+ for aluminum, so you need to compromise, you need to ensure charge neutrality, so you have the extra framework cations. So you can have different choice, like sodium, magnesium, calcium, etc. So you can already imagine this is a huge space, this is huge tunable space. And not to mention, although only 250, 240, or 240 topology has been reported, there are more than 100,000 distinct topologies has been predicted. And MOFs are emerging class of materials, and they are composed by metal nodes and organic linker. As shown over here, this is MOF5. And there are more than 10,000 MOFs has been reported. More than that, much more than that. And orders of magnitude more possible structures has been predicted. And not just about these two class of materials, like we can also have cups, etc. And there was also one of the really nice webinar talk or more talking about cups, and the audience can refer to those webinars. So as you can tell, these materials that have really interesting properties, they can be certainly used for separation, storage, and they are also highly tunable. So this is an opportunity, apparently. So we have a bunch of possible structures, and they have a variety of applications, like gas separation, as I say, carbon capture, natural gas purification, paraffin-olefin separation. They can be also used to do the liquid or water filtration, like water desalination, externalization to separate alcohol and water, or even recently very hot topic, water harvesting, to harvest water from the air to produce clean water, or even catalysis. So the main research theme in my group is mainly about computational materials discovery and design, given we have so many materials, so many applications. So our goal is trying to accelerate the discovery of materials. And the tools we are mainly doing, they are actually molecular simulation that belongs to statistical mechanics. And we do Monte Carlo molecular dynamics. We also do ab initio calculation, like DFT calculations, or machine learning. So as I said, allow me to emphasize again that my group, we do not do any experiments. So we are trying to use these state-of-the-art computational approaches and to evaluate or to investigate new materials and trying to predict new materials. And this has been one of our major goals. So just a brief introduction. So in my group, we conduct a lot of large-scale study to study promising adsorbents. We also conduct a lot of studies and trying to understand whether or not we can use porous materials as membranes for like externalization, water desalination. So I should mention that we also study polymer membranes. Although they are not really belongs to porous materials, but this has been always an interest in my group as well. So we also conduct studies on materials for catalysis like alkane cracking. And given we are a computational group, so we are also trying to develop better methods, such as we are trying to develop ways to better parameterize intermolecular interaction. In simulation, in order to make accurate predictions, we need to properly describe inter or intramolecular interactions that require what we call force field parameters. And how can we assign the force field parameters? And this has been a big question, right? So we try to develop ways to assign accurate potential, even including using machine learning. We also develop means to better, more quickly assign partial charge, how to better describe small molecules, and also trying to develop means to better simulate the association of complex molecules. And also, finally, but it's still not the last but not the least, that is, we also attempt to use simulations and trying to help develop characterization techniques to characterize materials, which will be the topic for today, as I showed you earlier for the title of the talk. So that is, we are trying to help the development of better characterization technique for surface area. So in today's webinar, I will be mainly talking about some published works from my group and also with collaborators apparently. So they are listed over here, and I will talk about the outcomes of these studies in a way that kind of like a journey we have gone through from many years ago to right now. So I should mention that these studies are mainly collaborative with the host today, Professor Zhong from Pusan National University. And I also want to acknowledge again my students, Dr. Arch Datar, who was my former PhD student when I was still at the Ohio State University. And he was the main person in my group for the study. Of course, I also want to thank my previous master student, Priya Shina, she was the first one to work on this at OSU. The importance of surface area, without saying, I believe that you probably will agree with me, but just according to some prior studies, for instance, from a study published in 2016, we can see that this is the excess hydrogen uptake in weight percentage versus the BET surface specific about the specific area of the materials. You can see there's a really strong positive correlation. So roughly speaking, if you have about 500 meters of the surface area, and you probably will have 1 weight percent of the hydrogen uptake. So this highlights the importance of surface area. So when we develop a new materials and trying to for use in storage applications, it is probably a good idea to maximize the surface area. But don't get me wrong, surface area is not everything, but it is a key contributing factor to a promising materials. So also by Snow and co-worker, they also published really nice work with the results shown here. The y-axis is the hydrogen deliverable capacity. The x-axis is the surface area, color-coded by void fraction. But let's omit the void fraction for now. I just want to draw your attention that it's really positively correlated or to a certain extent to the surface area. Of course, other factors like void fraction appears to also play a role. But the slide here just want to highlight the importance of surface area. So when we synthesize the materials, we need to know the surface area that also nicely inform the potential of the materials for storage, right? So in light of this, in the literature, there has been numerous attempts to synthesize high surface area materials. Like summarized as reported about 10 years ago by Yagi and co-worker, as you can see that before MAP, like zeolite materials, they tend to have a fairly small surface area. When I shouldn't say small, it's fairly moderate surface area, like 1,000 meters square per gram. But for MAP, as you can see that the surface area keep increasing. And one of the recent study, 2018, DUT60, the surface area was characterized to be as high as 8,000. So we have been talking about surface area, but the key right now is how surface area is determined. That's the key of today's talk. So normally after we synthesize the materials and researchers may confirm SRD, etc., and they will probably also most likely also measure their surface area to characterize their surface area. So typically what they do is after properly activating the sample, they will measure the dissociation isotherm of nitrogen at 77 Kelvin. So the P over P now will be 1 bar will be the boiling point, or argon at 87 Kelvin. So we will get a nitrogen or argon dissociation isotherm that is loading versus pressure as shown over here. This is one of the examples. And then we will apply what we call the BET equation. And the BET method is nearly exclusively adapted in the field, apparently. So this is the BET equation. I will talk about this later on. But the key right now is that we are going to fit the isotherm to the BET equation in order to find what we call the QM, which is the monolayer loading in the BET equation, which represent the first layer coverage. And as long as we multiply this number by the area of the sorbate, we get the monolayer coverage area. That's the idea. All right, so let me just talk about the next slide will be simpler. Again, this is the BET equation, or more specifically, I should say this is the linearized BET equation. So when we represent equation in this form, it should be linear. What I meant is that if we plot the left-hand side versus our relative pressure, it should be a straight line. So in this equation, the Q is the major loading. That is the loading which what we measure in the experiments. And P over P now is the relative pressure all the way from 0 to 1, although here show 1 bar, but P over P now will be just 1. And QM is what we call a monolayer loading, as I just mentioned. And this parameter C, you can consider this more like a ratio of the first layer interaction to that in the subsequent layers. A key important message to point out is that this is the BET equation. It's meant for a flat surface, but right now we are not talking about a completely flat surface. We are talking about nanoporous or microporous or mesoporous materials. So the surface will never be just not idealized. So that also means that this equation, in principle, if you have a flat surface and you can just have a straight line in this linearized BET, but in reality, you don't. So when you apply the BET equation, the really important aspect is that you need to select a linear region. You need to decide you want to fit to the BET equation, fit to the isotherm to which region, and you consider that as the BET applicable region. As shown over here, this isotherm, the blue dot, we essentially only select this more like an orange color region, and we fit to the BET. And we consider this region is what we call a linear region. Back in about 2007 and by Rockwell, and there have been a really famous 4 consistency rule has been proposed to determine such a linear region. And the first rule is that this term Q times 1 minus, relative pressure should increase as P over P non increase. And this is more like the numerator should increase as the denominator increase. And by doing this, you will only be able to, with this, and you will be possibly having a really linear. Otherwise, if this increase, this decrease, or this increase, this, I should say this way, if this increase, this decrease, you are going to get a quadratic relationship. And C should be greater than 0. That is more like by the model assumption, or we believe the first layer, it should be stronger than the subsequent layers. And the third rule is that after you select a linear region and you fit to the BET equation and you determine the BET monolayer loading, in this case, the value is about 110. So you hope correspondingly, this number is within the chosen region. So it's more like a self-consistency. You will determine monolayer loading is within your chosen region, which makes sense. The fourth rule is that given we are fitting to a BET equation, so you can also have a BET the isotherm described by the fitted BET. So we can also calculate the pressure per the fitted BT corresponding to the determined BT monolayer loading, and you will also get a corresponding pressure point. And you want the pressure point here is equal to the P3, which is the pressure corresponding to the actual isosome. So this represent how well, more or less represent how well your BT fitting is, right? And typically it's not perfect, so we hope that the rule was stated as it should be within 10%. So I will argue that the first and second rules, they are more or less more like a physical or mathematical significance. So we have to follow that anyway. The third and fourth is more like a self-consistency criteria. Okay, let's continue then. So let's now think about what is the BT area. As we can imagine, that is all about monolayer, right? Given we are determining this based upon monolayer loading. So let's just use this example again and to see, okay, so what does it mean? So this isosome was actually generated by molecular simulation. Remember, in molecular simulation, you can literally see where the molecules are and where are they adsorbed, right? So let me show you the configuration at the point where BT believe that this is the monolayer coverage, okay? So the black color is the framework, the structure, and this kind of like a brownish color. Each dot represent the adsorbent molecule. Here is argon. So please I would like to have your attention on here. You can see this cage. So you can see that the brownish color, they are really more like a first layer adsorption surrounding the cage, right? But on the other hand, by contrast, I should say this way, you can see here in this cage, it's actually not the case. So aside from adsorbing surrounding the surface, you have a bunch of adsorption at the center of the pore. So essentially those pores are more or less like condensed. So this is actually in direct violation of what we believe to be. We are hoping that this loading is more or less a monolayer, but in principle, you have a possibility that this point that you have the pore has been condensed. So this tells us that perhaps BT is actually not that reliable. So this finding was actually, we published this result in 2019. I should actually mention that there are a variety of prior studies also noticed this and reported this as well. And I will also briefly mention this later on. So in light of this, actually, we decided to conduct a large-scale, what we call the pseudo experiments. That is, although actually in the past, BT has been reported to be able to accurately predict the surface area, but some studies also said that no, BT may not be reliable. So at that point, we decided to conduct a large-scale study. That is, we try to study hundreds of months with diverse structures. And so we are trying to evaluate whether or not BT is really reliable. So over here, given of course, one can argue that we can do experiments, but that is quite challenging given that it's because that maybe there are some activation issue, etc. So here we use simulation, given we know the crystalline structures and we can run molecular simulation to compute the adsorption isosomes. So this allows us to be in a really good position to investigate or systematically evaluate such a phenomenon. So as I say, a large-scale pseudo experiments employing molecular simulation, and we compute argon adsorption isosome, non-nitrogen, for simplicity, because argon the computational cost could be much lower. And also, given we are going to do this kind of systematic evaluation, so we certainly need to have, references. So given we are doing simulation, and we also know where the molecules are, so our benchmark reference, we have asked for using what developed by Sner and co-worker, published in 2015, what they call the true monolayer area. We know the configuration, so we can really analyze the location of each molecules from the surface or from the wall. So we can just say that, okay, within a certain distance, that will be the first layer of the solution. So you can really quantify what is the monolayer loaded. So we use this as a benchmark reference. So the key message of this slide is that we examine more than 200 structures with diverse structural features, and their dissociation isotope were computed by molecular simulation. And also from molecular simulation, specifically from the configuration, we can also know the true monolayer loaded. So we can analyze the dissociation isotope by BET and compare with the true monolayer loading. That's the idea. So from the previous case, this case, the true monolayer loading is actually here. And the BET determined to be here. So you can already see that it's almost more or less more than 50% overestimation, given this structure include the condensation inside the monolayer. So for the webinar, I also prepared 2 slides to briefly talk about the simulation we are using. It's what we call Monte Carlo, and Monte Carlo simulation is mainly for probing equilibrium properties. So for a dissociation isotope, so the simulation actually is quite straightforward, and you can imagine that we are actually really trying to do experiments using simulation. So in simulation, we know the atomic structure of the framework. So in our simulation, we have a domain to be the atomic structure of the framework. And this is a gas phase of the solution, so we also imagine that outside of the framework, there is an infinitely large reservoir, and here using CO2 as an example, a given pressure and temperature. So that will be a given pressure point. And so we start to conduct what we call a Monte Carlo attempts. That is, we said, okay, we are trying to insert a CO2 into the domain. And at the same time, we also conduct some attempts to remove the CO2. And the key is that we do this millions of times, millions of attempts. And at the end, we essentially just trying to average out how many molecules on average in the system. So that will be our uptake. So it comes like experiments, right? You put a sample, you wait a really long time, and then you try to determine how much weight has been increased on the sample. So you may be thinking about, well, so how can I decide whether or not the insertion should be accepted or removal should be accepted? It's all based upon statistical mechanics. It's based upon thermodynamics. This is a two-phase equilibration. So it's all about chemical potential equilibration. And the structure is is rigid, so it's a constant volume. And the temperature for the two-phase equilibration will be also constant. So this is what we call a grand canonical ensemble. So what we call a grand canonical Monte Carlo simulation. So we can derive the insertion from n particle to n plus 1 particle. This is the acceptance probability. For the deletion, this is another probability. So we just follow this rule. This is derived from thermodynamics. So for the interest of the time, I really couldn't dive into that much details, but there was also I remember that Professor Sofia Claro, she also gave a really nice webinar on the simulation techniques. In her webinar, she mentioned that. And also for the CO2, for those molecules inside the framework, we also need to conduct a translation, like a randomly movement around or rotation, etc., trying to probe the entire possible configuration. So in this simulation, you will notice that we care about U, which is the interaction, a lot. In these simulations, we need to properly describe intermolecular interaction in order to make accurate predictions. And typically, we do Lennard-Jones or Coulombic interaction. As long as we are able to properly describe intermolecular interactions, the simulation and experiments should be on top of each other. This is for CO2 in zeolite as an example. So a really nice work published by Professor Greg Zhong, our host, and his co-workers in 2022 also showed a really nice agreement between the nitrogen dissociation isotope at 77 Kelvin between simulation and experiments as shown over here for a really famous mob called DUT23 as shown over here. So this is just trying to convince you that what we are trying to do here, the pseudo experiments, is not just put some random isotope. Those isotopes, they should be fairly reasonable and very reliable. Anyway, so let's go back to the outcome of the evaluation. It's interesting. So here, the y-axis is the BET area based upon the simulated isosome. The x-axis is the true monolayer area. So the parity line is here. I also highlight the deviation minus 20% means that BET is underestimates. Underestimates the area, and the positive is overestimates apparently. So you can see that, BT does overestimate, but they tend to be fine when they are applied to materials of small or relatively small surface area or intermediate surface areas. When you apply to really large surface area materials, as you can see that, the BT does overestimate quite a bit. And this is our previous example I just mentioned earlier also fell into this category, right? So let's have a closer look on what's going on. So we noticed that, I should also mention at this point that other researchers also mentioned this, also noticed this phenomenon, as will be talked about later on. One of the key, contribution is what we call the pore filling contamination. As I said that one cage, they are really monolayer formation, but the other cages, pore filling has occurred. So the monolayer just include those that have been condensed, which is not monolayer at all. That just caused a significant overestimation. I believe this can be understood. And as I say, a similar observation was also reported by Sner and co-worker in their true monolayer work, as mentioned previously. When you have a combination of mesopore and large micropore, and this bigger circle represents the degree of overestimation, so you can see that become pretty severe. That is, the large micropore, the mesopore, they are still monolayer formation, but the large micropore has been condensed. So we just include a bunch of condensed, those adsorbates that have been condensed as the monolayer, which is not making any sense. But essentially, this is the how the method will determine. Interestingly, we also noticed that it could be also due to what we call the pore filling indistinguishability. According to the meaning of the term, that simply means that the monolayer formation and pore filling, they cannot be distinguished. That's the idea. So this goes back to a study, actually my first postdoc when I was at TU Delft. We also report this phenomenon later at that time. That is, at that time, we use graphene sheet as the model system, as the porous materials model system. So we modulate the separation distance. We compute their argon and nitrogen adsorption isosome, and we determine their BT surface area. As compared to, at this time, we compare to their geometry area. Given the graphene, it's really easy to compute the area, right? And we also noticed that, let me have your attention here, around pore size to be about 10 angstrom, there's a significant overestimation. BT say more than 4,000, but in reality, it will be only about like a 2,000. And we found a phenomena, as I said, due to this distinguishability problem. And let me show you the isosome first. So this is the isosome for different separation. Let me have your attention on the 9.9, which is this point, highly overestimate point. And you can see the isosome is small, and then please see my cursor, and then condensed. It's more like, okay, we more or less having like a Langmuir type. No adsorption, slowly adsorb, and then condense. When you have a larger pore size, like let's say 12.85, this upper triangle, you will be small and then have a first step, you can see here, and then having the second step. It looks reasonable when you have a larger pore, so it's more like we have a monolayer formation. And this diamond, or not diamond, this square one is that it's more like a Langmuir type. But if we have a closer look at the system, this 9.91 actually corresponding to this configuration is actually not just monolayer. So the separation is big enough to have the first layer on the upper graphene, another layer, another monolayer at the lower graphene, but the center can also get filled up. Because the first layer of the solution, the other first layer of the solution also promote the third layer of the solution, so they just condense at the same time. So you have monolayer formation, you also have pore filling at the same time, so it becomes indistinguishable. So we have no way out. The BT will be always include this pore filling part. So you will always overestimate the area. By contrast, when we have slightly bigger one, as you can see, we can truly see the true monolayer will be the first step, right? So this is another reason we noticed that can be also linked to our prior study. I mean, this result is published in our 2019 paper. So given we now know that, okay, BT, they are doing fairly well for area up to this point, and they can overestimate. So we also still have quite a few things we would like to argue, we would like to talk about. That is, 4 rules versus only 2. So 4 consistency rules, I mean, the third and fourth, they are more like self-consistency, and the first 1 and 2, they are more or less like required. So what will happen if we only have the first and second rule? So it's interesting that you will have the area to be everywhere. Like the square one, let me use, please see my cursor. Let me use this structure as the example, one of the structures. This square one, as I pointed, this is the BT area following the 4 rules. But if we only follow 2 rules, we can find many, many possible linear regions. They can offer the surface area as small as 1,000 to as large as more like 7,000. So this is significant. So we actually tell this study also informed that, so we really employing all 4 rules indeed really help. So this is quite important given, so in the future, we will highly recommend if we are going to use BT, it's more likely that, it's preferred that we apply all 4 rules apparently. So this was actually also reported also, and there was also a report or more reports, several reports in the literature about this, as shown over here in ChemCom 2014. The authors also show that, when we can find different linear regions, they correspond to way different surface area, ranging from 5,000 to more than 10,000. So this highlights the importance of the 4 rules. So this is another question we would like to address by this large-scale study. And I also like to point out that even for this kind of relatively small area materials, you can see that they can also differ quite a lot. Oh, sorry, I probably need to speed up a bit. So we also try to probe the limit of the BT method. So given we know the true monolayer, right? So we can actually pick up, if we only follow the second or first rules, and we can pick up the best. We can find all the possible areas, so we can pick up. We also know the true area, so we can pick up the best. So this circle one is the best area. So the best area, so this is indeed inform the limit of the BT method. So this is the violin plot and showing the deviation. As you can see that the best BT does really do much better than the regular BT. Although there are still some deviation can be expected, but still the key is that there's no way that we can predict the best. So one of the research direction we have been trying to do, also reported in the past, is that can we find a better linear region? Can we find a better one? So for instance, using DUT23 as an example. So this is the isocene. And BT, if we satisfy 4 rules, that will be overestimate area by 25%. And this region is the best one. That is nearly on top of the true monolayer. So the question is that, can we find this region instead of this region? So in a prior study, we follow we use what we call the the authors call the S-association work, ESW. It is an equation shown here. It's an SS function as a function of loading, and then it's multiplied by delta U, the chemical potential change from the saturation state, which can be computed here. So for every single isocene, we can convert that into what we call an ESW plot. It's the SS function, S ESW function as a function of loading. So in their original work, they proposed that the first minima should correspond to the monolayer formation, and we found that, so this first minima indeed correspond to pretty nicely the base area. So we proposed that how about we modify the BT to be BT plus ESW? That is, aside from fulfilling the first and second rule, we also said that we need to choose a rule, choose a region that is where the ESW minima, first minima will locate, and then try to see which one can better further fulfill third and fourth rule. And we use the graphene, the nanotube as the example, so increasing from the small pore size to larger pore size, and small to larger one. So the true monolayer, we also show the true monolayer for each pore size, and you can see the BT also shown as the red one. You can see that BT can overestimate. So let me have you see the isosome. This is the isosome, show multiple steps. The first step corresponding to the monolayer, the second step corresponding to the pore filling, right? But the BT will choose this one, which caused the overestimation. But the ESW function, the first minima is actually the purple one. So it's this one. So which means that this may really help, at least for the case study. So we apply this to the real math. And here show a bunch of math. This show the BT. Inside the parentheses is the overestimation degree. So you can see that apply the BT plus ESW. It really helps for some cases. But there are some other cases that it does not. It does not really help. So BT ESW can only help in for some cases. And we found that when BT plus EW can help, that is when your isochron show distinct steps. So it will pick up the first step. It will help to pick up the first step corresponding to monolayer loading, not the condensation. But for those without a really distinct steps, it does not seem to help that much. Overall, for this case, I want to highlight that our tools can be employed readily, and we do publish what we call a script to estimate surface area of materials from the isosome sesame. You can see from our paper, and that is in the supporting information. You can use this development. And we are happy to see that this work has drawn some attention. So the next one is that we are thinking about how about BT is just a mathematical function. Can we just do machine learning? So we have isosomes. We can simply divide isosomes into several distinct regions. Or say the region 1, region 2, say we can describe isosome into, we can chop isosome, we can define features. And we just multiply by some coefficient and we create a mathematical machine learning function model, right? So what we did was that, okay, so we split our data and we split that into training and testing. And we apply what we call a lasso model to penalize unimportant features. And this is just for illustration. In the real model, we do consider the cross term, not just the linear one. So we train the model, and then we really train the machine learning model. And I'm eager to show you the performance. Again, this is trained based upon argon, and the argon overestimates our machine learning model perform really well, as shown over here. This can be also seen from the violin plot. In particular, please have a look at this large area region. You can see that the surface area is really just nearly 0% deviation. And this can be also applied to some known maps, as shown over here, like a DUT 16. The BT will tell the surface area is as high as 8,000, but true monolayer is only about 5,000, and our machine learning model also informed is 5,000, which is quite nice. So this can be an alternative to BET. And we also use this model to apply to nitrogen. So we select like 70 structures. We compute the nitrogen adsorption. We also see the BT. We can see the BT again, highly overestimates. And over here, we directly use the argon-based machine learning model with a correction on the area ratio. And we have a new model, but it's based upon argon. We did not retrain the model. You can see the performance is actually really nice. So this tells us that we can just apply the model to nitrogen. So just again, this is our Sesame 2.0. So you can also have the code from our supporting information. And then you can use this development from our work with Professor John. So actually, the previous conclusion lead to a really important and really interesting study we conducted in around 2022-ish. That is, as you may remember, in IUPAC 2015 report, and there are a few recommendations. One is 4 consistency criteria must be fulfilled, indeed true. And the recommendation 2 is use argon instead of nitrogen. It's because nitrogen has quadrupole moments, so they may have parallel or perpendicular configuration that may affect their packing. But interestingly, from a machine learning model, we can simply scale the area to use the argon model to nitrogen. That may indicate that it doesn't really matter that much to use either nitrogen or argon. In fact, recent experimental study does report that, okay, so nitrogen and argon determine BT area, they really do not differ that much as I shown over here. They're almost the same. But nonetheless, we attempt to study this phenomena in detail. So we firstly study a graphene structure that has been always our favorite, and to start from simpler materials, a graphene surface, and then with a different separation, and we try to study the phenomena to compare nitrogen and argon. We use simulation again. And for nitrogen, we can quantify their adsorption angle. If they are 90 degrees, that means that they are perpendicular to the surface. 45 is the TL 45 degree, and 0 is parallel. So our first study, we try to change the separation, and we try to enhance the interaction. Here, we simply enhance the Lennard-Jones parameter for the dispersion for the epsilon, for argon and for the nitrogen. But here show the nitrogen result. So this is different separation. This is different interaction strength between nitrogen and the surface, increased by 10 times, which is actually way beyond realistic, by the way, but to probe the limit, this will work. So you can see the distribution. They more or less tend to center at 0 degree. That is 9 flats, which is making sense. You have a flat surface, nitrogen would like to 9 flats. When you increase the interaction, the angle, average angle becomes smaller as you compare from here, 15, 10, and less than 10. So they tend to 9 flats, which makes sense given we have stronger interaction. And this is the true monolayer area we found determined from those configurations. As you can see that there's a consistent trend that, okay, so when we increase the interaction, the area increased. So although the angle become 9 more flat, but because the interaction becomes stronger, so the packing become more efficient, so the area increased. But this occurred also to argon too. So as a result, the difference between the two actually doesn't change that much. So the surface interaction itself, if that surface is homogeneous, it doesn't really change the difference between the two. It makes the nitrogen to have a higher packing efficiency. It also increased the argon's case too. But given the hypothesis is that we are having a perpendicular versus parallel, so it regards charge, right? So we modify the graphene, the toy system, to add off-site, the pseudo site, to only have charge. So that is shown over here. This is a carbon 1. If we assign this to be positive 4 charge, and then we have the nearby 3 carbon to each one have -1, and also the offside M, which is perpendicular to the layer, to also have -1, to create a dipole on the surface. So this can create a more polarized, I shouldn't say polarized, it's the heterogeneous or non-homogeneous surface for nitrogen to dissolve. So on charge, again, 9 flat. Charge, you can see, is bimodal, right? We can see some configuration become perpendicular right now. Some configuration, they are still, parallel. So this actually is in agreement with that, the IUPAC report that indeed we can have some perpendicular. And the average angle increased from 21 to 25. And the true monolayer, they also differ a little bit. And for argon, there's no difference because charge doesn't influence argon. But still, if you compare the two, it doesn't really differ that much. Of course, this observation indeed show that the configuration, indeed, they will change the perpendicular and parallel. But as a net, it does not really change the overall surface area that significant. And this may be subject to the density of the charge island, if you really have a surface to be all allowed perpendicular or all allowed parallel, that may make a difference. But in reality, can we really have such a structure? For one, MAF74, it has a really high open metal side density. And as shown over here, for nitrogen adsorbed onto open metal side, they tend to be perpendicular. For those two non-metal, they tend to be parallel. And in the structure, the nitrogen and argon, we found that they only have 2% difference in their BT area. So we apply this to, then finally we applied this to more than 200 MOFs with diverse structures. You can see here, BT area from nitrogen adsorption, BT area from argon, they are essentially on top of each other. And this is the average angle. You can see that actually the average angle among these different structures, they tend to be fairly similar. So our conclusion is that nitrogen and argon probably it doesn't really differ that much in terms of their ability to produce surface area. And providing nitrogen could be more, it's supposed to be much cheaper compared to argon. So nitrogen could be still a decent choice. As a conclusion, I'm sorry for the overtime. I mean, it's been like 15 minutes. So I want to highlight that the applicability of the BT method to MOFs appear to be reasonable. But for those with really large surface area, the BT may overestimate by maybe 100%. And the 4 consistency rules, they really help. At least you can have a more consistent result prediction. So it's better to compare among these different groups. Otherwise, it becomes a pick and choose. That you have so many linear regions. And the third one is, as I showed you, that nitrogen and argon actually do not really differ. The area do not show a notable difference. I also want to say that the machine learning based model, which our developments, we believe that it could be a really good alternative to the BT method. And finally, I want to highlight that all our developments can be readily employed. And as I just mentioned, we call this as the Sesame. As I just mentioned, now you can find the software provided in our publication. We have Sesame 1.0 or Sesame 2.0. And also, we also actually, last year, Professor John and his coworker, and also including myself, we put together a web-based interface as shown over here. And the more details can be seen from this publication and the QR code. And this is the address for the website. So as shown, if you log in, you can see the screen like this one, and then you can upload your own isosome. And if you want to see the format for the isosome, you can click the example isosome, and you can download the format, and then you can put in your data, and then you can upload. Click here to upload, and then you can run the calculation. And here will tell you the BT is automatic. It will tell you the ESW. It will tell you the BT ESW result. It will also tell you our machine learning prediction. So we sincerely hope that you will consider using this tool. This is actually a video, but I think for the interest of time, I think this is really easy to understand, easy to use. And there are also some, you can see over here, there are also some options. You can see, you can turn something off and turn some function off, turn some function on, etc. Without further ado, I want to thank you for your attention. I really appreciate the opportunity to speak for the webinar. Thank you. I'll stop here.
Okay. Yeah. Thank you. Thank you, Li-Chiang, for excellent seminar. It was very thorough explanation of the BT area, which is a lot of interest to many of the IAS member. We have a question from Yu Chen on YouTube. So I'll read the comment. So it says, I would like to know that when determining the true monolayer area from the simulation results, how do we determine the distance from the surface at which adsorbates are considered to be in the monolayer adsorption? And he said, since, as you mentioned, it might be easy to overestimate the monolayer uptakes and consequently the overestimated monolayer area. So if you could maybe comment on that. Yeah.
Yeah, this is a good point, and I must apologize first that I forget the details we use, but I remember that it's based upon the interaction. It depends on the epsilon value between the sorbate and the surface atom. So I remember that that is within the potential well distance. But for details, I remember that we follow exactly what's used reported by Snow and co-worker in that Jack's paper in 2015. As I say, I do remember it's based upon the potential well location. Professor Zhong, maybe you have some, you can also add something, given you are also
I think that is correct. Yeah. So I think you look at the absorber base that's located near the potential well of the surface atoms and count them. That's the strategy.
Yeah, so that can really capture supposedly capture the first layer, given the potential well will be around the first layer.
First layer, yeah. Okay. So I guess it's probably except Japan, Korea, and Taiwan, not many people is able to watch the webinar because of the time difference. So I think that's the question that we had from YouTube. So thanks again, Li-Chiang, for excellent seminar.
Thanks.
And then I'm gonna switch to the so anyway, yeah, thanks Li-Chiang for excellent seminar on the surface area determination of porous materials. We also thank all the attendees for joining us in the webinar and hope that it was both educational and enjoyable. I'm pretty sure it is. The edited version of this webinar will be posted on the IAS YouTube channel and Bilibili with an announcement on the IAS Twitter feed or X feed. The hope is that the work discussed today will be a useful resource for the absorption science community in the future. And our next confirmed IAS webinar will be given by Gennady Gore, which I also have a personal interaction with on March 20th at 2 p.m. UTC. And another one will be in April by FS Coder in April 24th, also 2 p.m. UTC. Announcements regarding the next webinar and the other IAS online events will be posted on our Twitter or X feed and through the IAS mailing list. With that, we thank you again for joining us, and thank you, Li-Chiang, for excellent seminar.
Thank you.
And we hope that you'll join us again soon.
Thank you.
Thank you. Yeah.